Hi everyone, I am Dr.A.RAKINI, Assistant Professor of Chemistry, A.D.M. College for Women, Autonomous, Nagapattinam. Now I am going to present my topic on nuclear chemistry. This topic present in 2nd BSc Chemistry, Unit 3. Okay, let us see the introduction. But what about nuclear chemistry? Nuclear chemistry deals with nuclear reactions or reactions that happen inside atoms. Nuclear chemists may be found in different areas of research, including nuclear imaging in medicine or nuclear engineering in power generation. Nuclear chemistry is the study of the physical and chemical properties of elements which are influenced by changes in the structure of the atomic nucleus. It also deals with the energy released from nuclear reactions and its uses. Radioactive elements. Nuclear chemistry is the subfield of chemistry dealing with radioactivity, nuclear processes and transformations in the nuclei of atoms, such as nuclear transmutation and nuclear properties. It is the chemistry of radioactive elements such as the actinides, radium and radon, together with the chemistry associated with the equipment such as nuclear reactors, which are designed to perform nuclear processes, and then these include the corrosions of the surfaces and the behavior under conditions of both normal and abnormal operations, such as storing an accident. An important area is the behavior of objects and materials after being placed into the nuclear waste storage or disposal site. Next one, natural radioactivity. Natural radioactivity is the radioactive found in nature as uranium, thorium ores and natural nuclear fuels. The radioactive waste is produced during mining and ore milling, and the waste mostly contains natural radioactive substances such as uranium, thorium, radium, radon, etc. Nuclear chemistry is the study of reactions that involve changes in nuclear structure. The chapter on atoms, molecules and ions introduced the basic idea of nuclear structure, that the nucleus of the atoms is composed of protons and within the proton and neutrons. Next one, recall that the number of protons in the nucleus is called the atomic number of the elements, and the sum of the number of the protons and the number of the neutrons is the mass number. Atom with the same atomic number but different mass numbers are isotopes of the some elements. We often use the term nucleus and identify it with the notation. There is a formula of X, A, Z, where X is the symbol for the element, A is the mass number and Z is the atomic number. Okay, next one is a very important of alpha, beta and gamma rays. Okay, gamma rays are a weightless packets of energy called photons. Unlike alpha and beta particles, which have both energy and mass, gamma rays are pure energy. Gamma rays are similar to visible light but have much higher energy. Gamma rays are often emitted along the alpha or beta particles during radioactive decay. During the radioactive particles like alpha, beta and gamma rays are emitted by the atom to the unstable atom trying to gain stability. Hence the atomic and evenly decay by emitting a particle that transforms when they are unstable and transform the nucleus into a lower energy state. Next one, this process of decaying continues until the nucleus attains a stable stage, and there exist three major types of radiations emitted by the radioactive particles, namely alpha, beta and gamma. These radiations are released from the nucleus of an atom. Their behavior differ from one another through all the three causes some ionization and carry some penetration power. Let's discuss the properties of beta, alpha and gamma one by one. First one, alpha rays. Alpha particles are positively charged and made up of 2 protons and 2 neutrons from the atom's nucleus. Alpha particles come from the taking of the heaviest radioactive elements such as uranium, radium and polonium. Even though alpha particles are very energetic, they are also heavy that they use of their energy over short distance and the unable to travel very far from the atom. The healthy effect from the exposure to the alpha particles depends greatly on how a person is exposed. Alpha particles lack of energy to penetrate even the outer layer of skin. So exposure to the outside of the body is not a major concern. Inside the body, however, they can be very harmful if the alpha emitted inhaled or into the body through a cut. The alpha particles can damage sensitive living tissue. The way of this is large heavy particles causes damage, makes them more dangerous than other type of radiations. The ionization, the cause are very close together. They can release all their energy in a few cells. The result is more damage to cell and DNA. Next one is a beta rays. The beta particles are small, fast moving particles with a negative electrical charge that are emitted from an atom's nucleus during the radioactive decay. These particles are emitted by the certain unstable atoms such as hydrogen 3 and carbon 14. Beta particles are more penetrating the alpha particles, but they are less damaging to living the tissues and the DNA because the ionization they produce are more widely spaced. They travel further in the air, the alpha particles, but it can be stopped by a layer of clothing or by a thin layer of the substance such as aluminium. Some beta particles are capable to penetrating the skin and causing damage such as skin burns. However, as a alpha emits, beta emitters are most hazardous when they are inhaled. Next one, gamma rays. The gamma rays are weightless pockets of energy called photons. Unlike alpha and beta particles, which have both energy and mass, gamma rays are pure energy. Gamma rays are similar to visible light but have much higher energy. The gamma rays are often emitted along with alpha or beta particles during the radioactivity decay. Gamma rays are a radiation hazard for the entire body. They are easily penetrative barrier that can stop the alpha and beta particles with the skin and clothing. Gamma rays have the much penetrating power that is several inches of the dense materials like lead air. Even a few feet of concern may be required to stop them. Gamma rays can pass completely through the human body. As they pass through can cause the ionization that damage tissues under DNA. Next one, properties of alpha particles. The alpha particles are strongly ionizing that cannot penetrate very far into the matter and are brought to rest by a few centimeters or of the air and less than a tenth of a millimeter of the biological tissues. Next one, properties of a beta particle. Because of their low masses, they less and the loss energy fast and when they touch with a matter and travel in a random manner through air or then things. Next one, the beta particles are far less ionizing than the alpha particles and as a result to far less damage for the same amount of energy deposition. They generally have air ranges of tens of centimeters. This is energy dependent and a material range of a few millimeters. Next one, properties of gamma rays. Gamma radiation is a kind of electromagnetic radiation. It is also known as EMR. They are identical of X-rays, which is the exception of they are released from the excited nucleus. Electromagnetic radiation may be thought of the stream of photons, which is the massless particles that flow to wave-like pattern and the speed of light. Each photon has a certain quantity and is a bundle of energy, and all electromagnetic radiation is made of the photons. Gamma ray photons contain the most energy in the EMR spectrum and the shortest wavelength. Next one is very important one, it is here half-life period. The half-life are previously known as half-life period as one of the common terminological used in physics. to describe the radioactive decay of a particular samples or elements within their certain period of time. Students of nuclear physics will come across the term often while they are studying the subject. However, this concept is also widely used to describe various types of decay processing, especially decay. And apart from the physics, the term is used in the medical science to represent the biological half-life to certain chemicals in the human body or in drugs. Half-life definition. It's one of the most important 2-mark question. Half-life definition. The half-life is normally defined as the time needed by a radioactivity substance or one of the atoms to disintegrate or transform into a different substance. The principle was first discovered in 1907 by Rutherford. This is usually represented by the simple use or T off. And help you understand the concept better, we take a radioactive element which has a 1 hour and then half life. It is in this has the 1 half will decay within the hour and the remaining would decay with the another hour. The equation that arises here is why did not the remaining materials not decay in the hour. Next one here. Well, if the radioactive elements is taken in a gas where half of the atoms have decayed after one of life, it would be proper to assume that they have a life except at the average levels as well defined. The atoms within the mean life, that is much longer than their half-life. This would mean that after half-life divided into 2, which is a natural, which of the mean life. And then another hand, half-life is often defined to term of probability. Next one, half-life period is a formula. The students will find below the formulas or half-life used to describe the decay is a substance. The formula of NT equal to N naught of and then T by T of. Okay. The NT is a quantity of the substance remaining. N naught means initial quantity of the substance. T means time elapsed, and the T of is a half-life of the substance. Next one important of the 10-mark questions is a Bajan-Jody in the group displacement law. Bajan-Jody group displacement law. The law of radioactive displacement, commonly known as Jody's Bajan's displacement law. It can be started as the radioactive element and the isotope that occur in each radioactive decay is different for the different types of decay. And this interchanging of the element to another was called the transmutation of elements. Radioactive decay is a long and elaborate process that occurs in nature. The decaying of the radioactive elements leads to the formation of a new all-bond beta particles, which in the turn leads to the radioactive decaying. The transmutation of the element is the process that occurs when the element changing from one state to another. So, when the transmutations of elements occurs, the particles changing into the isotopes and they can go back into their original state. In radioactivity, these transmutations of the elements leads to the formations of the particles such as alpha particles, gamma particles and beta particles. In radioactivity, alpha, beta and gamma decay common occur when the radioactivity elements break down during the pumped. Next, in the state of Jody and Bajan's displacement law, as we know that during radioactivity decay, some particles pumped into the different forms. This Bajan's displacement also said the same. The Jody, the Bajan's in the binding was later clubbed together to want to radioactivity and nuclear physics are said Jody-Bajan's displacement law. It was studied by both scientists that when a nuclear particles disintegrates breaks into the many particles. This was termed a transmutation of particles and isotopes were also discovered during this study. Moreover, it was found that when alpha decay happens, the atomic number gets reduced by 2 and the mass number also gets reduced by 4 of the parent isotopic taken. In beta decay, there is, however, no change observed in the mass number of the element. Atomic number increased by 1. The law of radioactive displacement, also known as a Bajorn's and Jody's law in the radioactivity. Nuclear physics is a rule governing the transmutation of a element storing radioactivity decay. It is named after Jody and Bajorn, who independently arrived at about the same time of 1913. The law described which the chemical elements and isotope is created during the particular type of radioactivity decay. In alpha rays, an element created with the atomic number less 2 and a mass number less by 4 of the parent isotopes. The beta decay, the mass number remaining unchanged while the atomic number becomes greater by the 1/10 of the parent isotope. In the corresponding to beta decay or electron emission, and the emission the only form with beta decay which had been observed when Pajanas and Jody proposed the law in 1913. Later, in the 1930, the forms a beta decay known as beta plus decay. This is also known as positron emanations and electron capture were discovered, in which the atomic number becomes less by 1 than that of the parent isotope. Next one, Haiger-Natal law. It is an important 5-mark question. The Haiger-Natal law or Haiger-Natal rule relates the decay concept of the radioactive isotope. With the energy of the alpha particles emitted, the roughly speaking, it is stated that the short-lived isotopes emit more energetic alpha particles than the longer-lived ones. The relationship also shows that the half-life depended on the decay energy, so that the very large changes in the half-life make the comparatively small differences in the decay energies and the alpha particle energy. In the practice, and this means that the alpha particles from all alpha emitting isotope across many orders of magnetic of different in half-life. All nevertheless have about the same decay energy. Next, the formulated of in 1911 by Haiger and Natal as a relation between the decay constant and the range of alpha particles in air. It is a modern form. The Haiger-Natal law is a log 10 and then T of equal to A z by root of E plus B z. There T of is the half-life, E is a total kinetic energy, the alpha particles and the tartar nucleus. A and B are coefficients that depend on the isotope's atomic number Z. The law works best for nuclei with even number, the even atomic mass. The trend is still there, the even, odd, even and odd nuclei, but it's not as pronounced. Next one, isotopes. The isotopes, atoms with the same number of protons but a different number of neutrons are called isotopes. And they share almost the same chemical properties but differ in mass and therefore their physical properties. And there are stable isotopes which do not emit radiation, and they are unstable isotopes which do emit radiation. Next one, the radiation, the number of protons with the atom's nucleus is called, it is a atomic number, and it is equal to the number of electrons in the neutral. It is also known as non-ionized atom. Each atomic number identifies a specific element but not the isotope. On atoms of a given element may have a wide range, and it is a number of neutrons. The number of nucleons, both proton and neutrons. The nucleus is the atom's mass number, and each isotope of a given element has a different mass numbers. For example, carbon 12, carbon 13 and carbon 14 are 3 isotopes of the element carbon with the mass numbers 12, 13 and 14 respectively. And the atomic number of carbon is 6, which means every carbon atom has 6 protons, so that the neutron numbers of this isotope 6, 7 and 8 respectively. Next one, isobar. The isobar, atom of chemical elements having same atomic mass but a different atomic number are called isobars. The sum of the number of protons and neutrons together form the atomic mass. Therefore, we can also say the number of nucleons present in the nucleus is equal to the atomic mass of the atom. It will have the some number of nucleons, the number of protons and neutrons along with the but the number of nucleons or the sum of the protons and the neutrons in the isobar will also be same. Isobar also always have different atomic structure because of the different in atomic numbers. The number of neutrons makes up to the different in the number of nucleons. Therefore, they are always the different chemical elements having the same atomic masses. The isobar has a different chemical properties. Another example is here the argon and the calcium with the atomic number of 18 and 12 respectively. However, they have the same atomic number is mass of 40, and furthermore sometimes they are a series of the element that has the same atomic mass. For example, cobalt Cu and the nickel Ni, cobalt copper Cu and iron Fe have the some atomic mass 64, but the atomic number is various. And the next one, isotones. Isotones can be defined as the two or more nuclei of atom consisting of the same number of neutrons. In simple words, atoms with the same number of neutrons but a different proton are termed isotones. Therefore, we see two conditions for the atom or nuclei to be termed as isotone. Number one is that the atom or nuclei should have the same number of neutrons. Number two, it is here that they should have the different number of protons. Atoms, these isotones may have the different atomic numbers and different atomic masses. And the element of next one, element of isotones. First one is a neutron. Neutrons discovered in May 1932 by the English physicist James Chadwick. It is a neutrons where a newly fundamental particles divided after any charges. It means that these particles locked both under positive charges and negative charges. They are the neutral in charges, so he named them the neutrons. In simple words, they are a kind of the subatomic particles with no charge. For the conversions of the momentum and the energy, he divided the mass of neutrons. He also noticed that the mass of neutrons is very close to the mass of a protons. And then M1 equal to 1.00866, U equal to 1.67, and then 49 into 10 power 27 kg. The discovery of the neutrons to a better understanding of the atomic number, the number of protons and electrons, and atomic mass, the total number of neutrons and protons. The number of neutrons is on the atom or nuclei is represented by N. Next one is protons. The protons were discovered in 1886 by the Holstein. The word protons means first in Greek. This hence the Rutherford have this the name of 1920 to the hydrogen nucleus. Protons is a subatomic particles having a positive charge. The positive charge of the protons is equal in the magnitude to a unit of the electron charge. The mass of the proton is equal to 1.672 62 in 10 power 27 kg. One or more protons are present in the nucleus of every atom or nuclei, and they form an important part of the nucleus and are represented by the symbol P or P+. They play an important role in the identification of atomic numbers. Example of isotopes. The isotones are atoms having a similar number of neutrons and different protons. There are several examples of isotones. Some of the examples of isotones include carbon 12, nitrogen 13 and carbon 14. All three of them have their 6 neutrons and the number of protons in carbon is 6. The nitrogen is 7 and the oxygen is 8. The boron 12 and carbon 13 are isotones. Both have their 7 neutrons, so they are isotones. And the sulfur 36, chlorine 37, the argon 38, potassium 39 and calcium 40 are all isotones of a 20 because they have 20 neutrons. And hydrogen 2 and helium 3 are the isotopes of neutron 1. Beryllium 9 and boron 10 are isotopes of neutron 5. And carbon 13 and nitrogen 14 are isotopes of 7. Krypton 86, atium 89, zirconium 90, molybdenum 92 and radium 88 are isotopes of the neutron 50. Uses of isotones. Isotones can be found in various neutron applications. A typical example is the production of a technetium-99 used in medical imaging, which is produced by the neutron radiation of molybdenum nitride targets. The isotope that leads to the higher cross sections produce more products and yet therefore are more efficient. Another application is on the production of the fissionable of the materials of nuclear weapons. This can be done by the exposing of a heavy isotope, usually uranium-239 or a plutonium-239, 35 and 39 to fast neutrons ray. The bumped with the deuterium accelerated the particles, the acceleration of the cyclotron. The resulting compounds nucleus emits more neutrons on the average than it is observed, increasing the changes of the successful fission. In addition, it is used of military applications. Isotones can be used to neutron absorb for the reactor control. Generally, the reactivity increases and the fraction of a reactor 4 is reduced. However, too few neutrons will be absorbed to maintain a certain reaction. Isotones that cannot absorb a neutron are only with a long decay, with will thus the reduced reactivity. Next, very important topic of nuclear isomerism. And the nuclear isomerism is a condition where atomic nucleus have the same number of protons and neutrons but different life terms, and they occur when the nucleus are a different unstable quantum states and TK2 lower excited states or the ground state. Metastable states. The nuclear isomerism are metastable states, meaning their excited states have the high lives that are 100 to 1000 times longer than other excited states. Different energies. This year, nuclear isomer always have different energies, unlike chemical isomers which have a similar or identical energy state. Gamma decay. When a nuclear isomer decay, it usually emit or the gamma ray as a proton and a neutrons, and then rearrange themselves to have the of excess energy. This is called gamma decay. Next one of the important question is a radioactive TK series. It is a radioactive TK series, also known as a TK chain. Is a sequence of a radioactive TKs that leads to a stable form. Each series has the unity chain of TKs, and the TK produced within the chain are always radioactive. The final atom in the chain is the only one that is not radioactive. There are 4 radioactive TK series: the thorium series, the neptunium series, and the uranium series, and the uranium actinide series. Parent and the daughter nuclei. Each series is made up to the parent nucleus at the first number with the long half-life, and the series of daughter nucleus that leads to the stable end product. The end product of the uranium series, the actinide series, and the thorium series is the stable isotope of it. The neptunium series ends with the thallium-205, the half-life. The half-life is the time it takes for the half of the radioactive atoms to decay. Some radionuclides have the half-lives of seconds, while others have the half-lives of the millions of years. And next one, important 2 mark questions. Magic numbers. The nuclear magic number is defined as the number that deals with the both protons and the neutrons, properties and the electrons and their interactions. 2, 8, 20, 28, 50 and 82 and also 126 are considered the magic number in nuclear physics, and they are numbers that can be well organized in the atomic cells. Next one, nuclear stability. The nucleus of an atom occupied in thin fractions of the volume of an atom and contains the number of protons and neutrons at the caps of the given isotope. Electrostatic repulsions, while normally the causes of positively charged protons and repel each other, but the nucleus does not fly apart because of the strong nuclear force and extremely powerful but the very short range attractive force between the nucleons. The next one is a neutron-proton ratio. It is also known as NP ratio. The neutron-proton ratio is here of on the atomic nucleus is the ratio of it is a number of neutrons to it is number of the protons among stable nuclei and naturally occurring nuclei. This the ratio generally increases with the increasing atomic number. This is because electrical repulsive forces between the proton scale with the distance of different than the strong nuclear force attractions. In particular, most pair of protons in the large nuclei are not far apart, such that the electrical repulsion over the strong nuclear force, then thus the proton density is a stable larger nuclei must be the lower than the stable. The smaller nuclei where more pairs of the protons have an appropriately short range nuclear force attractions. Binding energy. The binding energy amount of energy required to separate the particles from system of the particles or to disperse all the particles of the system. Binding energy is especially applicable to the subatomic particles in atomic nuclei to electrons bound to nuclei in atoms, and then atoms and the ions bound together in crystals. The nuclear binding energy is the energy required to separate an atomic nucleus completely into it is the constituent protons and the neutrons are equally the energy that is would be liberated by the combining individually protons and neutrons into a single nucleus. The hydrogen 2 nucleus, for example, composed of one proton and one neutron can be separated completely by the supplying 2.23 million electron volts of energy. And conventionally, when you are slowly moving the neutron and the proton combine to form a hydrogen 2 nucleus, 2.23 microvolt are liberated in the form of gamma radiation. The total mass of the bound particles is less than the sum of the masses of the separate particles by the amount of equivalent as they expressed in the Einstein's mass energy equation to the binding energy. Electron binding energy, also called ionization potential, is the energy required to remove an electron from an atom, molecules or an ions. In general, the binding energy of a single proton or neutron in a nucleus is approximately a million times greater than the binding energy of a single electron in an atom. Thank you.